Hello, everyone. My name is Calvin Bideman, and today I will be talking about multicriteria cuts and size-constrained k-cuts in hypergraphs. This work was done with Karthikeyan Chandrasekaran and Chao Xu. I'll begin by introducing the single criteria min-cut problem. In this problem, we're given a graph with positive costs on the edges. For any S subset of the vertices of the graph, we define the cut induced by S, written delta S, as the set of all edges that have one endpoint in S and one endpoint in V minus S. The partition S and V minus S can also be called a cut, but for our purposes, it's more convenient to view a cut as a set of edges. A min cut is a cut of minimum total cost. For instance, in the given graph, the red edges form a min cut. Note that the min cut need not be unique. Two classic questions about the min cut problem are, given a graph, can we efficiently find the min cut? And how many min cuts can an n-vertex graph have? Now let's talk about how to generalize this problem to multiple criteria. In this setting, we're given a graph where each edge has t different costs associated with it, given by cost function c1 through ct. There are several different ways to measure the quality of a cut in this setting, and we're going to talk about three of them. I'll define each of them in turn. First is parametric min cuts. We say that a cut is a parametric min cut if it's a single criteria min cut for some linear combination of the t cost functions. So for instance, the red edges here are a min cut under the single criteria that's equal to the first cost function plus half of the second cost function. Next are Pareto optimal cuts. We say that one cut dominates another if it's at least as cheap in every cost function and strictly cheaper under at least one of them. A cut is Pareto optimal if no other cut dominates it. For instance, the red edges here form a Pareto optimal cut. Their total cost is 5, 5, and every other cut has a cost of at least 6 in one of the two criteria. Note, however, that this cut is not a parametric min cut. For any way of choosing weights for the two cost functions, either the cut induced by B or the cut induced by C will be cheaper than this Pareto optimal cut. Before introducing multi-objective min cuts, I need to introduce B multi-objective min cuts. In the B multi-objective min cut problem, we're given not only a graph with edge costs, but also a budget vector of t-1 different budgets. We say that a cut satisfies the ith budget if its cost under the ith cost function is at most bi. And our goal is to find a cut of minimum ct cost among those that satisfy all t-1 budgets. So for example, the red edges here are a 9 multi-objective min cut because their c1 cost is at most 9, so they satisfy the single budget in this case. And the c2 cost of 3 is as small as possible, subject to satisfying the budgets. Note that the B multi-objective min cut is not Pareto optimal because swapping AD for BC would give a cut with the same C2 cost and a smaller C1 cost. Finally, we define a multi-objective min cut as a cut that's a B multi-objective min cut for some B. So in the multi-objective min cut problem, like in the parametric min cut and Pareto optimal cut problems, we are not given a budget as part of the input, just the graph with an edge costs. So how do these different measures relate to each other? Well, it turns out that every parametric min cut is Pareto optimal, and every Pareto optimal cut is a multi-objective min cut. However, as the examples have shown on the previous slides, these containments can be strict. So what are the generalizations of the classic questions about min cut? The first question we might think of is the algorithmic one of, can we efficiently find a parametric or Pareto optimal or multi-objective min cut? But it turns out that this question isn't interesting because if we simply choose weights for the different cost functions arbitrarily, then we can get a single cost function, apply a single criteria min-cut algorithm, and find some parametric min-cut. And by our observation, this parametric min-cut is also Pareto optimal and multi-objective. So the only interesting find a cut problem is, given a graph and a budget vector, can we find a B multi-objective min-cut efficiently? The structural question, however, is interesting for all the kinds of cuts. In particular, it's interesting to ask if the number of multi-objective min-cuts in a graph is necessarily polynomial. Because if it is, that implies that the number of Pareto optimal and parametric min-cuts is also polynomial. Finally, if the number of multi-objective min-cuts is polynomial, then we can ask if it's possible to enumerate all of them in polynomial time. In our paper, we answer all three of these questions in the affirmative. And I'll illustrate the first two in this talk. Now, let's review prior work on the single criteria min-cut problem. It's been known since the 70s that the number of min-cuts in a graph is O of n squared. And this bound is tight because the cycle has omega n squared min-cuts. More recently, this n squared bound has been generalized to constant rank and even arbitrary rank hypergraphs. A hypergraph is a generalization of a graph where instead of edges consisting of exactly 2 vertices, there are hyperedges consisting of any number of vertices. The rank of a hypergraph is simply the size of the largest hyperedge. For our multi-criteria problems, Karger showed that the number of parametric min-cuts in a graph is O of n to the t plus 1 and omega of n to the t over 2. We will talk about his techniques later in the talk when we explain how we derive our bound. For the special case of 2 cost functions, IC, McCormick, Majab, and Queran showed that the number of Pareto optimal cuts is O of n to the 5th. And IC, Majab, and Ravi showed that the number of B multi-objective min cuts for a fixed B is O of n to the 2t. To our knowledge, there was no prior work on the number of multi-objective min cuts without a given B. However, we note that Rico Zenklusen derived a bound the same as ours independently that we learned of after the publication of this paper. Our main contribution is an O of n to the 3t minus 1 bound on the number of multi-objective min cuts. We will show this in this talk. Note that this also implies a matching bound on the number of Pareto optimal cuts by our previous observation, and that this n to the 3t minus 1 bound matches the previous bound of psi et al. For the t equals 2 case, as well as the n squared bound for the t equals 1 case. Our contributions also generalize to constant rank hypergraphs with a more complicated LP-based analysis that we won't have time to discuss in this talk. For arbitrary rank hypergraphs, all the multi-criteria problems remain open. Now, we'll talk about our argument to prove the n to the 3t minus 1 bound on the number of multi-objective min cuts. To start, we want to review Karger's bound on the number of parametric min cuts, since our argument is inspired by his. Karger's argument is, in turn, based on his own proof that the number of min cuts is O of n squared. Karger's proof is based on his random contraction algorithm, which simply repeatedly selects an edge in proportion to its weight and contracts it, that is, merges its 2 endpoints, until the graph has only 2 vertices. and then it returns the resulting cut. And this algorithm outputs any min cut with probability 1 over n squared. And since it outputs only a single cut, this means that the number of min cuts in the graph is at most n squared. To bound the number of parametric min cuts, Karger gave another random contraction-based algorithm that outputs O of n to the t minus 1 cuts, such that every parametric min cut is output with probability 1 over n squared. And this shows that the number of parametric min cuts is at most n squared times n to the t minus 1. Similarly, we give an algorithm based on random contraction that outputs O of n to the t minus 1 cuts such that every multi-objective min cut is output with probability 1 over n to the 2t. And this will show that the number of multi-objective min cuts is at most n to the 3t minus 1. So it remains to give such an algorithm. In order to do that, we will start by defining an algorithm for the B multi-objective min cut problem, where we are given t minus 1 budgets. And our goal is to find a cut that has minimum CT cost subject to satisfying all t minus 1 of the budgets. So our algorithm is based on random contraction, and our base case is 2t vertices instead of 2. In order to choose which edge to contract, we define sets UI, where UI is all of the I infeasible vertices. That is, vertices that satisfy the first I minus 1 budgets, but violate the ith budget with the single vertex cuts they induce. UT is the set of feasible vertices. That is, vertices which induce cuts that satisfy all of the budgets. We choose whichever of these t sets we've just defined is the largest, and let I be its index, and then contract an edge chosen in proportion to its CI cost. Let's go through a simple example of how this algorithm works. So suppose we have this 6-vertex graph. To begin, we compute the sets U1 and U2. C, and in this case, our B is 4. C and D both induce cuts of weight 8. So they are 1 infeasible vertices. A, B, E, and F, on the other hand, induce cuts of weight at most 4. So they are all feasible vertices. Since the size of U2 is larger than the size of U1, we pick an edge to contract based on the C2 costs. Let's suppose we pick EF, one of the edges with a C2 cost of 2. Contracting it gives us a 5-vertex graph, and we recompute the UIs. Now U1 includes C, D, and the new vertex EF, while U2 includes only A and B. Since U1 is now bigger, we contract an edge chosen with probability proportionate to its C1 weight. Let's suppose we select CD, one of the edges with a C1 cost of 3. Contracting it gives us a 4-vertex graph, and since 4 is equal to 2t, we stop contraction and return a random cut. For example, we might pick the cut given by these blue edges, which is a B multi-objective min cut in the graph. All right, so what is the probability that a given B multi-objective min cut is actually returned by this algorithm? How do we analyze this? Well, one observation that we can make is that since the sets that we've defined partition the vertices into t sets, the largest of them, UI, must have size at least n over t. We also claim that for any vertex in UI, the cost of the cut that it induces under the ith cost function is at least the CI cost of f. To prove this, we consider two cases. If I is less than t, then v is I infeasible. So the cost of delta v is at least bi, while since f satisfies all the budgets, the cost under I of f is at most bi. On the other hand, if I equals t, then delta v and f both satisfy all of the budgets. But since f is a min CT cost cut satisfying all the budgets, the CT cost of f must be at most the CT cost of delta v. With these two observations in hand, we note that the CI cost of all of the edges put together must be at least 1/2 of the sum of the CI cost of all of the single vertex cuts by the handshake lemma, which is at least 1/2 of the total CI cost of all the vertices in UI. And by the claim, this is at least the size of UI over 2 times the CI cost of f. And by our first observation, this is at least n over 2t times the CI cost of f. This means that the probability that the first edge we choose is from f is at most 2t over n. And therefore, we can write the probability that f survives all rounds of contraction with this telescoping product that we can lower bound with 1 over n to the 2t. Thus, we have that any B multi-objective min cut has at least a 1 over n to the 2t probability of being output by this algorithm. In order to turn this into an algorithm for regular multi-objective min cut, where we're not given the budgets, we need to think about it from a different perspective. We note that at every step, we're picking which edge to contract uniformly at random according to one of the cost functions. This means that we could actually do all of the randomness up front and simply pick t random orderings of the edges, and then at each step use the UIs to determine which of the orderings to contract the next edge from. So if we view our example from this perspective, we pick two orderings, pi1 and pi2, where pi1 is chosen based on the C1 costs, pi2 based on the C2 costs, and then we compute our UIs. Since U2 is bigger, we contract the first edge from pi2. Then since U1 is now bigger, we contract the first edge from pi1 that hasn't already has its endpoints merged. So in this case, EF is gone, so we contract CD. So this algorithm runs exactly the same as the previous one, but now all of our randomness happens up front before we make any decisions based on the budgets. In particular, we note that we only use the budgets to select which ordering to contract from next. So if we want an algorithm for multi-objective min cut that does not take the budget as input, then we can simply try all possible ways of interleaving the permutations. Every possible way of choosing to contract from pi1, then pi2, then pi1, then pi1 again. If we try all those possible orderings, we'll definitely use the one that the B multi-objective min cut algorithm would do for any particular B, and we'll just return multiple cuts. In order to show that this algorithm does what we want, we need to bound the number of cuts that it outputs. So we need to ask, how many distinct cuts can result from different interleavings? And we note that the final cut that we output only depends on which edges we contract, not the order in which we contract them. And therefore, we can assume that we contract all of the edges that we're going to contract from pi I before we move on to pi I plus 1. So we can assume that we just start by contracting from pi 1. At some point, we move to pi 2, and so on. And the point at which we move on is when the graph has some number of vertices ni. So choosing an interleaving is equivalent to just choosing these stopping points ni. And there are only t minus 1 of them, because once we're contracting from the cost function pi t, we have to keep going until we get down to 2t vertices. So there are only O of n to the t minus 1 ways to choose interleavings that could possibly result in distinct cuts. Therefore, try all the interleavings and output all the different cuts you see algorithm outputs O of n to the t minus 1 cuts, while still retaining the n to the negative 2t chance of outputting a B multi-objective min cut for any B. So we've given an algorithm that has the guarantees that we were looking for, and therefore the number of multi-objective min cuts in a graph is O of n to the 3t minus 1. To wrap up, I want to discuss some of the other results that we show in our paper, one of which is a lower bound on the number of Pareto optimal cuts, and therefore the number of multi-objective min cuts in a graph. Recall that a cut is Pareto optimal if it's not dominated by any other cut. There's no cut that is at least as cheap under every cost function and strictly cheaper under at least one of them. Our construction with a large number of Pareto optimal cuts consists of two special vertices, u and v, and t different disjoint equal length uv paths. On the ith path, every edge has a ci cost of 1 and a cj cost of 1 over t plus 1 for every j not equal to I. Then any cut that includes exactly one edge from each of these paths will be Pareto optimal, because they're the only cuts that have a cost strictly less than 2 under every cost function. The number of such cuts is n over t to the t, which is omega n to the t. We also prove results on node budgeted variations of the multi-objective min cut problem. For details on the definition of this problem and our techniques, see our paper. They also use random contraction and interleaving. Finally, we address the S size constrained K-cut problem, where we are given constant lower bounds on the sizes of the sets in a partition, and we want to find a partition satisfying those lower bounds with minimum total edge cost. In conclusion, we have seen that the B multi-objective min cut problem can be efficiently solved by random contraction. And this algorithm, combined with the interleaving argument, shows that the number of multi-objective min cuts in a graph is polynomial. These results can be extended to constant rank hypergraphs through an LP-based analysis that we did not show. And arguments based on random contraction and interleaving can also address node-weighted multi-criteria cut problems. So these techniques are powerful and versatile. To finish, I want to mention some open problems. There's a significant gap between our upper bound of n to the 3t minus 1 and our lower bound of n to the t on the number of Pareto optimal and multi-objective min cuts. So a natural question is, can either of these bounds be improved? Another question is, do our structural results generalize to arbitrary rank hypergraphs? Is the number of even parametric min cuts necessarily polynomial in an arbitrary rank hypergraph? Our interleaving argument crucially relies on the fact that all the contractions we're performing are uniform, and uniform random contraction is insufficient to solve min cut in arbitrary rank hypergraphs. So new ideas are needed to solve this problem. And finally, the algorithmic problem of B multi-objective min-cut is also open in arbitrary rank hypergraphs. So resolving that would be another avenue of research. Note that parametric min-cut can be efficiently solved by simply choosing arbitrary weights. So the other cut measures are not interesting from an algorithmic perspective. Thank you for your time.